Alrighty, so let's take a closer look at some of the items from Chapter 7 about linear regression. Linear regression is probably the first tool that we're working with. We did talk about correlation a little bit last chapter, where this tool's really powerful, and we have to be really careful with it. It's just not something that we can just throw around and use everywhere. It really has to we have to make sure that we've got the appropriate conditions in which to use it. So let's take a closer look at that. And then once we've used it and done it, how good is it? Is it even worth using? All right. So when we're using the regression, again, it's kind of a quote here from Star Wars, but with great power comes great responsibility. So I always want to ask myself, does it even make sense? So even before I run the regression, does it make sense to do so? Once you start running the regression, take a look at that scatter plot. Does it really even make sense to continue? And then once you're done with it, how good is it? So we're going to walk through a little example here as we do that. All right. So again, before I even run that regression, does it make sense to do so? So I want to ask myself, am I working with quantitative variables? Again, because it's a mathematical procedure, I need to have those values in order to do that. And is it even reasonable for these variables to have a linear relationship? So let's kind of apply this to an example here. Can we reasonably predict the speed of a roller coaster based on the height of its initial drop? All right? And if I think about speed and height, those are two quantitative variables. And if I think about the relationship, I can certainly think that the higher the drop, the faster it's going to be. Is it going to be a linear relationship? I certainly see that there's going to be some sort of a positive association there, but I think it would probably be reasonable. I could also think from a physics perspective that I've got some sort of a velocity and I got gravity going on here, so it might not be linear, but it might be pretty close. So I think it's reasonable to move forward. So let's go ahead and do that. Okay, now, so should we continue? So once I start running this linear regression, what am I actually looking for? So I'm going to go ahead and make that scatter plot, and I want to, take a look at the scatter plot itself. Is it straight enough? In other words, is it relatively straight for me to be able to use a linear model? Are there any outliers that could possibly throw things off? Remember, I'm working with those means. I'm working with standard deviations, both which are susceptible to influence from large outliers. And this is a kind of an interesting one here. It's sometimes referred to as this process of fanning, or in the book refers to as does the plot thicken? I want to make sure that my data is relatively consistent throughout my line. I don't want to see my plot get fanned out. In other words, kind of where it just gets further and further away from my line as I go along the line. In other words, the model gets worse and worse. I want to make sure that things are relatively constant there. So here we go. Here is the scatter plot of the initial drop based the initial drop, in feet, and my speed in miles per hour. And I'd have to say that that looks, relatively straight. I think I do have kind of a few maybe values that are a little bit out of the pattern here, but other than that, things look pretty good. It doesn't appear to have any fanning to it, and it appears to be relatively consistent as I go across my line, across the data here. So let's go ahead and run that regression. So I'm going to go ahead, I ran my regression, and you can see it's actually kind of right in the middle of the lines that I drew here, and it looks pretty good, right? And here's the linear model that we got to go along with it. So I want to stop right here for a quick sec and talk a little bit about my linear model. Since it's a model, I should really put a hat on my variable of speed, and we'll take a look at my slope and my intercept. The intercept, as we've talked a little bit about, doesn't often have a relative meaning to my problem here. Now remember, this is where my x value equals 0. So I have a speed of 38 miles an hour, 38.5 miles an hour with no feet of drop. So that's probably not terribly realistic or terribly valuable. You can also take a look at the smallest drop in these roller coasters is down to about 50. So to go below down to 0 probably doesn't make sense either. Let's focus a little bit more on the slope. And here I have my slope is 0.1 4.8. And the interpretation of that slope, you really want to think about what my units are. So you remember that your slope has units, its change in y over your change in x. So it's reasonable to think about the slope with your y units over your x units. So we already know that the speed is going to be in miles per hour here. And then if I think about my x units are feet of drop. Well, if I just make a ratio out of that, I can interpret this as approximately a 0.18 mile per hour gain per 1 foot of drop. And if I write it out like that, it's really easy to make that interpretation. So, okay. All right, so now that we've run that regression, we want to take a look at and evaluate how good it is. So one of the first things I want to look at is that residual plot. And I don't want to see anything exciting here. I want to make sure that I got no patterns or bends or curves or fanning or outliers. I'd like to see, again, my data just kind of laying right across that line. I'd like to see, again, a uniform scatter throughout my line. And I would like to see most points pretty close to that line. That's my residual standard deviation. I'd like that to be pretty small. And then last but not least, I want to look at the R squared value. In other words, how much variation is being accounted for in my model. Let's take a look at that. So I'm looking at some JMP output here, and you're going to have a lab to do with this stuff. And it gives me a bunch of different plots, so I kind of cut and pasted a few here. So I have 3 different versions of my residual plot here. What I've got is the residual speed that I have for the predicted speed. I have my residual speed based on the drop, and this is the one that we've been referring to most in the book. So we'll take a closer look at this one. And down here we have kind of essentially it's a normal quantile or my normal probability plot that you saw previously when we were looking at assessing normality. Okay. And it actually gives me these little error bars or these error ranges here that I want to make sure all my dots kind of fall within there. And it's pretty close, okay? So this tells me that I have roughly a normal plot of residuals, which you can also see up here. So what I'm looking for is a relatively uniform scatter, and I kind of sort of have that. I may have a couple of outliers, and those are those 3 ones that we had seen before, all right? So that's what I'm looking for there. I don't see any bends or curves, so things look okay in that respect. All right. Okay. So last but not least, I'm going to take a closer look at that R squared value, and also take a look at that residual standard deviation of my residuals. So first off, the standard deviation of the residuals here, I have what's referred to as a root mean square error that appears, and that's very similar to the standard deviation of my residuals, and you can see that this is 4.9, and this is going to be in terms of miles per hour. So the typical distance from the model is about 5 miles per hour. So that's a relatively accurate predictor, okay? So what I'm going to take a look at now is this value of the R squared, this R squared value right here. R squared. And we can express this in terms of a percentage. I'm going to call that 83%. Whoops. 83%. And what that says, this 83%, it says that my model is accounting for 83% of the variability that I see in the speed. Okay? Now, if we were building a new roller coaster, and I asked you to predict what the speed of it was going to be, and I told you nothing about it, okay? Nothing about it, and you thought about the speeds of all of the different roller coasters that are out there, and here I have a box plot of the speeds of roller coasters, your best guess would be, what's the average? And this is the average speed, okay, of all 75 roller coasters that we have. So without any other information, your best guess at what the speed of a new roller coaster would be about 65 miles an hour. Well, if I told you the height of the highest drop, you would be able to make a more accurate prediction. In other words, some of the variability that I have here in speeds of roller coasters would be able to go away because you would be able to get more accurate. So if I take a look at my residuals, okay, this is again the distance that each one of these points is away from the model, okay, that represents the accuracy. And I can see that here. So now, if I account for the drop and predict the speed, I have a lot less variability. You can definitely see that. And I kind of put these guys on the same scale. I had to squish this down a little bit to make that work. Okay? So the model that I'm using based only on the drop accounts for 83% of the variability. That's pretty high. So again, that model is pretty useful. It's quite accurate. It gives me a decent representation, and it seems to fit my data pretty well. So I think all in all, that's a pretty accurate model, and again, a good predictor.